All right, tomorrow we're going to graph our kinetics data, and we're going to do the Visual MinTech lab. For Visual MinTech, you don't have to prepare your notebook for that. You know, we've been treating the Chapter 18 problems as ideal, but we know that things can deviate from ideal behavior. Did I talk about this yet? Not yet. And what Visual MinTech will do is it will treat them more realistically. And so let me show you what I mean by that. Okay, I didn't talk about the uncommon ion effect, right? I didn't talk about ion pairing, those types of things. No, I think, in one class I didn't. I'm pretty sure it was the afternoon. Unless does anybody remember seeing this? No, okay, then it was in the morning. I talked about this already in the morning last week, but I'll talk about it. When we treat it ideally, for example, PbI2, we assume that it splits up into Pb2 plus and 2 iodides. But what I mean by ideal, well, this splits up ideally. What I mean by non-ideal is sometimes, let's say the first iodide breaks off, but the second doesn't. And so what we call this species is like an ion pair. That is, the Pb2 plus and the iodide are stuck together as a pair. And so the whole thing is going to have a +1 charge. And then in order to break off that second iodide there, it has to collide with something, and then it can break off into two. Do we cover species like this ion paired species? Raheem talked about it? Okay. No, we don't, but here, this is a species, well, PbI2 is an ionic lattice, but what can happen is that a Pb2 plus can break off and 2 iodides can break off from the crystal. And this is actually PbI2. This would be like a molecular species, but really what it is a Pb2 plus paired with 2 iodides. And so you got this 3-ion cluster now that's paired together. You know, it's not like a real molecule with covalent bonds or anything like that. It's just paired ions. And this could break apart. It could break apart over to here, that is 1 iodide, and then that second iodide can come off, or both iodides can break off and come up back to here.
If it's just pure ions, what's connecting them together?
Just charge. You know, positive and negative attract each other. And so they're going to be held together by electrostatic attraction, but it's not a bond. You know, bond would be, well, the ionic bond is a very strong electrostatic attraction. These are weaker, but still they can happen to a small extent, which means that, you know, this is deviating from ideal behavior. We talked about this. Did you guys ever go back and read that the thing in chapter 13 about activities? Do you remember activities? Effective concentrations, the Van Hoff factor? We ever talked about that? This is way back in Chem 1A. You ever go back and look at this table back in chapter 13? Yes? I don't know. I think I asked a couple of times to go back and read. There's like 1.5 pages dealing with activity back in Chem 1A, chapter 13. And so when you go back and read it, you'll see the table like this. So what is this table telling you? There are 2 things that this table is telling you. What are they? Or maybe 3 things. I don't know. When you see a table like this, you know, the best thing to do is just try to summarize that table in your own words, you know, so that if somebody asks you what's happening in this table, you can tell them. It's like the acid-base chart, you know, or the redox chart. Yeah. So did anybody go back and look at this? No? Nobody? Well, this is ideal. For example, sodium chloride, you know, splits up into a sodium ion and a chloride ion, which is 2 particles. And so this is ideal. Magnesium sulfate ideally splits up into 2 particles, right? Magnesium ions and sulfate, and PbNO32 should ideally split up into how many ions? 3 ions, right? And so this is ideal. What are all these other numbers? All those other numbers are showing deviations from ideal behavior. That's what the activity is. Do you guys remember activity at all? Activity. For example, you know, K is actually the activity of the products raised to, you know, their power over the activities of the reactants raised to their respective power. The equilibrium constant, K, is based on activities. Activities are what? What are activities? The effective concentration. Effective concentration. Why effective concentration? Because you can have things that cause it to deviate from ideal behavior. What's the main thing that causes these deviations from ideal behavior? Well, back in chapter 13, they talked about the main thing, which was, does anybody remember? Not temperature. Temperature, like gases, you know. For gases, you know, for example, if you're to go to some planet out in the universe that's under, you know, tremendous pressure and low temperature, would you use the ideal gas law to calculate the properties of the gas on that particular planet? No, because those are pretty non-ideal conditions. You'd have to use something that calculates the properties of a real gas. Well, what causes those deviations for gases? So temperature is one, because, you know, and the pressure is the other. And why? Well, you can go back and look at it, why. But for solutions, what causes the deviation from ideal behavior? Primarily this. What is that? Interionic attractions. Meaning what? IMFs, right. So you have it. But it's not intermolecular, you know. These are interionic attractions. Do you see we have ion pairing occurring here, clustering. And so rather than behaving as separate individual ions, this behaves as a group, as a cluster. And so the effective concentration of this has just gone down because now they're clustered together rather than separate. And so rather than having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles independent, they're just acting as one group. And so what happened when we went from 10 individual ions to one cluster of ions is the effective concentration goes way down. This is the ion pairing effect. And so we talk about in here activity, right? effective concentration versus the stoichiometric. The stoichiometric concentration is the ideal concentration. So sodium chloride, the stoichiometric concentration was 2.00. But we see it can deviate, and that's what this chart's showing you. So what are the patterns in this chart? The patterns in this chart are the higher the concentration, the greater the deviation. So when we get to concentration 1 molal, it's effectively behaving as 1.81 particles rather than 2. So about 10% of the particles are clustered, paired, right? And so the higher the concentration, the greater the deviation. The lower the concentration, the more ideal it becomes. So infinite dilution, we expect solutions, all solutions to behave ideally. But you can see here, you know, is that deviation more significant for magnesium sulfate or less significant? For magnesium sulfate, rather than having about 10% of the particles paired like that, you have about 50%, right? And so, you know, here, the ideal concentration is 2, but its effective concentration is 1. Ideal concentration is 2, its effective concentration is 1. That tells you what? A lot of particles are paired or clustered. So these interionic attractions are significant. But so why is it more significant for magnesium sulfate than sodium chloride? Actually, I'm just curious, how many people actually went back and read this when I asked? Nobody? Wow. No gung-ho students. I said, go back and read this. It's only 1.5 pages. Not one student? Yeah, that's true, at least honest. Everybody already knows? Is that because you already know what activity is? Yeah? Okay. Oops, that's wrong. If you already know what activity is, then no problem. You don't have to go back. But this is where you're going to find activity. It wasn't talked about in Chem 1B. It was talked about in Chem 1A. But in Chem 1A, most people don't remember this. So it's good to go back and go through it. But anyway, let me just tell you then. Normally you would do this yourself, but the higher the charge, the worse the problem gets, right? And so you can see for magnesium sulfate, it's quite considerable. Also for lead 2 nitrate, it's quite high as well because it should be 3, it's 1.31. So it's due to the charge on those ions. And it makes sense because obviously the higher the charge, the greater the electrostatic attraction is going to be between the ions. Because all of a sudden if you make one of these a +2, you can double the attraction according to Coulomb's law. Now if you make this one a +2 and this one a -2, you're going to quadruple the attraction according to Coulomb's law. But what does that mean for us? What that means for us are we using activities in our calculations, or are we using just ideal concentrations? We're using ideal concentrations in our chapter 18 calculations. Well, what does that mean? That means that when we get a problem like PBI2, what did Rahim say about PBI2? The ion pairing? Okay. Did he say anything else? I mean, what do we do about this? What should we do about ion pairing?
We don't really consider it.
Yeah, we completely ignore it. If we completely ignore it, is that accurate? No, it means that, you know, it means our calculations are going to be off. Now, you know, if we have a +1 and a -1 versus a +2 and a -1, you know, it's going to be off more significantly. And so the higher the charge is, the more our calculations are going to be wrong, basically. And so this is what it means here. I can't scroll. I don't know why I can't scroll right. This says, okay, basically our calculations should be correct within an order of magnitude. You know, what kind of percent error is that? If we're close, you know, maybe we might be an order of magnitude off. If we're an order of magnitude or 2 orders of magnitude off, then what kind of percent error is that? It's huge, right? And so our calculations are going to be off. Our calculations are going to be off because we start to deviate, you know. And the more we deviate from ideal behavior, the more our calculations are going to be off. And so this is a problem because, okay, as long as we're close, within an order or 2 of magnitude, you know, we got a 10 to the third, 10 to the minus 3, but maybe it's 10 to the minus 5 is the correct answer, then we're happy. At least we aren't more. If we're off by a factor of 1,000, 10,000, 100,000, a million, if we're off by a factor of a million, would you be very happy with that calculation? No. And so these are some serious limitations here. And so what are we doing with all these calculations? Well, you know, some of the calculations, well, are going to be somewhat close. Others are going to be way off. So if we're calculating like lead-2 nitrate or magnesium, whatever, lead-2 nitrate's soluble, unfortunately. The lead-2 chloride, lead-2 iodide, yeah, we're going to be off. And the higher the charge is, the more off we're going to be. But there's not much we can do, otherwise things get too complicated, because in order to properly solve this, you know, there are a lot of equilibria here happening. So for example, PbI2, you know, a lead and 2 iodides might split off, or a lead and an iodide, and that other iodide breaks off completely. And so we got multiple equilibria, and these 2 equilibria are connected here as well. They don't show it. And then if we have more iodide laying around, we can form other species too, because iodide can act as a ligand. And PbI2, can act as a Lewis acid, and we can attach another. So here's a triiodo plumbate 2 ion. And it turns out we could fit 4 iodides around that lead as a complex. This would be the tetraiodo plumbate 2 ion. A 5th iodide doesn't really fit on that. And so look at how many equilibria we have. Now, in order to solve this, can I do this stepwise? No, I can't do this stepwise. Can I do this combined? Combined's a new method we learned. Can I do it combined? No. There's only one way to solve all these equilibria, and that is simultaneous. We got to solve these equilibria simultaneously. And so what we do in chapter 18 is we limit ourselves to, you know, quote unquote simple problems, right? And hopefully we aren't too far off in terms of error. But is that very useful? Well, yeah, if you can figure out what's going to happen to an order of magnitude or 2 orders of magnitude off, maybe that's okay. But what if we want something more accurate? Then what do we do? Well, we got to consider all these possibilities. Not only do we have to consider all these possibilities, which we will, but there's other things that can further complicate the issue, and that is something like this. This is showing the solubility of silver chromate. If you look at the solubility of silver chromate in pure water, it's here. If I add common ion, like chromate, so I dump in a whole bunch of potassium chromate, then it's going to precipitate out more silver this way. And so solubility goes way down here. This is called the common ion effect. This is a precipitating agent. And so I could use chromate to precipitate out more silver. The silver concentration goes down as the solubility goes down. But it turns out that silver chromate is actually more soluble in KNO3. And so why would it be more soluble? In fact, it's more soluble in any salt, as long as it doesn't impact the particular salt. And so it doesn't have to be KNO3. It could be NaNO3 or something else that won't precipitate out silver. And so what else would precipitate out? Most things would precipitate out silver. And so if I'm looking at silver chromate solubility, this is going to split up ideally into one silver and, not one silver, two silvers and a chromate. Do you expect this to deviate from ideal behavior, and why? This is what we say. This is ideal. It's stoichiometric, right? These are the stoichiometric concentrations. But would you expect this to deviate? Yes, I would expect this to deviate because of chromate. Chromate's at -2. That's going to have a strong attraction for silver, so I'd expect some ion pairing to occur, some clustering. Does that make sense? And so, yeah, this is kind of a high charge here. We expect some ion pairing. So our calculation here is going to be off because are we going to take those into consideration? Are we going to use activities? Have we used activities yet? No. It's not that they're hard to use, it's that they're beyond the scope of this class. It would require additional calculation. And so we aren't going to use them. We're going to keep things simple. But keeping things simple means we're going to have some error. So we could calculate the solubility of this in pure water. Initially, there's 0 and then plus 2s plus s, and so at equilibrium we got 2s and s, and then if I'm given the KSP, I can figure out what s is, the solubility, right? Or likewise, if I know what the solubility is, then I could figure out what KSP is. But that's not taking into consideration any of the ion pairing. But in addition to ion pairing, ion pairing that's discussed in chapter 13 in Chem 1A is different than this, because ion pairing can happen to a lesser degree here. So for example, this would be the solubility of pure water, but what if I'm looking at the solubility, like what is it more soluble in? In pure water or sodium nitrate? Well, does sodium nitrate impact this equilibrium? Is there any kind of Le Chatelier shift? Sodium nitrate contains sodium ions and nitrate ions. So is that going to shift the equilibrium one way or the other? No, it shouldn't. Versus silver nitrate. If I tried to dissolve silver chromate in the solution of silver nitrate, AQ, will this impact the equilibrium? Yeah, if I have silver ions here, that's going to shift it to the left, meaning the solubility is going to go down, right? But here, in sodium nitrate, we see a small increase in solubility. In silver nitrate, we see a large decrease in solubility. So this is what this graph is showing. If we were to add a common ion, any common ion, it could be silver, it could be chromate, we're going to see a sharp decrease in solubility. But why do we see this increase in solubility with things like this, uncommon ions? This is called the uncommon ion effect. The reason we see that is because of this. With the uncommon ion do is they're going to do a Le Chatelier's-like shift. So for example, if I have silver ions, what's going to happen is the nitrates are going to cluster around the silver. And form a little cluster like that. And so what happens is that this is what we call free silver ions, and these silver ions here have been surrounded by nitrates. This is not a complex, like these nitrates aren't actually bonded to this. These are just ion-ion attractions or ion pairing attractions, right? And so as the free silver is being removed because it's being clustered around here, it cannot precipitate out with chromate because you got all these nitrates, right, interfering. But the nitrates aren't hard to break off. And so if the nitrates aren't that hard to break off, then it's only going to be a small increase in solubility, not a large. If those nitrates really get stuck on here, like for example, if I didn't use nitrate, if I used ammonia or cyanide, then those would really attack the silver and make this hugely soluble. We call that KSPF. Right? This is not nearly as great as KSPF, because it's just a small clustering effect. And the same thing with the chromate, this can go both ways. And so the chromate can be surrounded by the cation, sodium ions in this case. And so if the sodium ions cluster around the chromate, then that's going to reduce the chromate, the free chromate ion concentration, and shift the equilibrium to the right. And so as I increase, you can see over here, as I increase the concentration of things like sodium nitrate or potassium nitrate or lithium, whatever I want, as long as it doesn't precipitate or complex with any of the silver ions or the chromate ions, that's going to result in an increase. And so the higher the concentration of uncommon ion, or i.e. the salt, the greater the solubility. That's what we see in this chart here. Are we going to worry about this uncommon ion effect? Not in our calculations. The only time you'd worry about it is if I ask you a question like this on the test, or the homework asks you a question like this. What is silver chromate most soluble in? Is silver chromate most soluble in water, sodium nitrate, or silver nitrate? Most soluble. It'd be most soluble in sodium nitrate. Why? Because of the uncommon ion effect or the salt effect. Now, how are we going to put that into calculation? We aren't.